name is Vivian. It's an honor to be here. I haven't been here at Reionization for a very long time. And a good daughter, I always return home. And Reionization is my home. Will always be my home. And UOB will be my dynamic fixed point, where I always come for, counseling. Let me just tell a little bit some slides about UOB. So we started working with him when I was an undergrad, and I have to say I was in classes with physics. I was taking lots of math classes. I was not happy with physics, and you also saw talent and determination in me, something that I didn't see in myself. He talked to me about physics. I got engaged again, and the rest is history. And even after I left PJ, his door was always open. He always responded to my emails. I know. People know how I write emails, like, Earth is not fall, something like this, and it's all very patient. I keep saying this over and over again, that with all the exceptional education I got here, and I said this every year at the University of Chicago, I will never be able to be a successful student of Wayne. I will never be able to do a successful postdoc. And I keep saying this, that my education was built on the shoulders of 4 giants in cosmology, and you are from each one of them. And this was the Cosmo course that allowed me to not fail all of these ones. And gave me the basis for this one. So, thank you. Okay, you are for everything. So, there's some philosophy here. So, I will try to convince you that first, there's a lot of good research to be done in the early, intermediate, and late-time universe, but also the universe is connected, and therefore, uncertainties in one of these phases can propagate to influences in the other ones. By early universe, I mean everything that happens before the emission of the CMB photons. Intermediate, it's everything between the CMB photons, the beginning of the epoch of reionization. Late-time universe is everything after the epoch of reionization. So let's start with early universe. I'll try to condense this talk to 20 minutes, so it might be a little bit hard. So we know the basic cookbook of the seeds of perturbation that later on created the galaxies, the clusters, is the inflation. And if you see the temperature power spectrum of the CMB, which is just the Fourier transform of the 2-point correlation function of the CMB intensity map, we got these oscillations that have well-defined positions and well-defined relative amplitudes. And this oscillation can be decomposed in 2 parts. The first one that comes from inflation, which tells the seeds, and the transfer function that tells you how the coupling between baryons and photons evolved that perturbation the seeds on. And for the seeds, we usually assume that the power spectrum, the Fourier transform of the 2-point correlation function, is given by a power law, and it has an amplitude and a tilt. This is 2 of the 6 parameters of the Lambda-CM model. And one of the questions that I asked a lot with collaborators, with my advisor during my PhD is that are there examples that violate these basic pictures? And the answer is yes. So by the way, this is just my publication name, some translations. And the answer is yes, there's many examples, systems that oscillate, systems that break the power. I'm just showing one of them where here is the power law that we got from the basic cookbook of inflation, and the shades are what I reconstructed from the cosmic microwave background, and there's well-known mismatch in power between large and small scales. But the question I want to mention is different. Let's do the following exercise. Examples like this can show the inflation can be complicated. It can be more complicated than we thought. So, if that's true, can this mismatches of inflation, or our knowledge of inflation, be connected to the intermediate and the late-time universe? So that's the connection I want to make between the universe at 1 second and the universe at 5 billion years old. And to get that, sorry for this, I have to tell how the CMB measures dark energy. And it measures dark energy by predicting, not measuring. People got this wrong. CMB predicts what is the value of the Hubble constant. And you do this by this combination of measuring the position of the peaks, which gives you this combination. This is a very good exercise. If you don't know how to get, you should do this exercise. And the other one, it tells you how you get from the relative amplitude of this versus this peak. And this gives this combination. If you divide, you can predict H naught. And the exercise I have done with collaborators is the following. What is the H0 that we predicted if we assume the basic cookbook of inflation versus more general models? And our answer is this. So this is if you assume the double map range, and here is the basic models of inflation versus this more general model that has the suppression of power, and you can see solid versus shades that the value of H0 changes. And that's important because this is the biggest task that we have for the Laplacian model, and today there's a 4.3 sigma tension between the CMP and the local magnet. So we are reaching the 5 sigma tension, so we should be very aware of this problem, and I'm just showing that inflation can change a little bit, not too much, the prediction from the cosmic microwave background. Any questions? Okay, so let's go to the second part, the intermediate universe. Here in this talk, I will focus on the atom of reionization. So what's the atom of reionization? Is the second phase where the universe were ionized. It was ionized in the past, it became neutral, and then ionized again. And for us that measure the cosmic microwave background, we see the atom of reionization because basically we have this telescope that measures two-point correlation functions and correlates the intensity and the two polarization states of the CMB. And between us and the CMB, there's this sheet of free electrons that comes from reionization. So this is basically a Jackson problem. And if you do that, you see that once you have the temperature pulse spectrum, more reionization, more free electron damps the oscillation of the CMB. It doesn't damp everywhere. You can see that this is constant, and that is related to the horizon size of reionization. And therefore, we can use temperature and polarizations to measure that polarization. There's something, another thing, there's some degeneracies to the temperature that makes this problem hard. It comes from the fact that inflation can raise this power back end. So there's this well-known degeneracy between inflation and reionization. But that can be partially broken by one of the effects that we measure. This is the CMB lensing. So basically what I'm showing here is how the degeneracy works. It's AF e to the minus the optical depth. And I'm showing two modes with different optical depth, and unlensed CMB and lensed CMB. And you can see when you add gravitational lensing, you get differences that are in phase with the peaks. And that's not a coincidence. The lensing transfer powers from the peaks to the troughs. So it makes this to be pi difference to the Beagles itself. So that's one of the ways that we measure the optical depth. Another way is the polarization pulse spectrum. So here I'm showing the E modes. And I want to show a few things. So I want to show here is the exercise where I took the ionization fraction of electrons and I made delta functions of perturbations a function of redshift, and I see how the polarization changes. And I want to emphasize here that the CMB can not only measure the total optical depth of reionization, but it can also measure its evolution. So therefore, reionization at redshift 7 will produce a remarkably different signal than reionization at redshift 49. Okay, so based on that, we could, using the plan 2015 data, we published an analysis that is a lot of people off in Europe, where we reanalyzed the Planck data, and we found that the main claim that they have, that there was no reionization above redshift 10, at least for the 2015 data, was false. And we did find hints of high redshift reionization. You might believe these or not, things has changed a little bit in 2018, but the question I want to ask is also similar. Given that reionization can be complicated, how can we connect it back to the early universe? Can it change inference that we make about the early universe, propagating these errors not only forward in redshift, but also backwards? And the answer is yes. So here is the same plot I showed below, the same blue shades, but now I just didn't paint them. And the red one is when I redo the analysis with this new model of reionization, and you can see that the amplitude of that reversal for inflation changes. And that should not be something mysterious. Both inflation and the CMB changes the relative amplitude between the Sachs bulb and the oscillations. And therefore, if you change tau, that should feed back into inflation. Okay, last part, late universe. So we know there is an acceleration. We know the supernova are too faint. So here's the vast population of supernova to the late, called the N-team supernova. And here is prediction that I did by hand, more or less, what would happen if omega matter equals 1. And you can see that at redshift 1, the supernovas are around half of magnitude off. And if you tell someone like Adam Rees that he's wrong by half a magnitude, you lose a lot of recommendation, let's say this. So there's ways to study dark energy. You can study model by model. You can do F of R modified gravity. You can do coupled dark energy. We have people that have done great models of both. But I want to take a more generic approach to this problem, and I want to ask first a particle physicist, what are the minimum physical assumptions that you can make about dark energy? And if you ask them, they will give you these 4 answers here. You will assume that general relativity is right. You will assume that there's no interaction, no Feynman diagrams between dark energy and dark matter, dark energy Starman model, and the dark energy only clusters at the horizon side. It has to close at the horizon side because GR, there's an energy conservation from GR. Here I'm assuming that it's moved well below the scales of the horizon. So there's no dark energy galaxies or clusters, for example. And if you assume that you can make all these interesting models, you can make them SDM, quintessence, phantom, you can have negligible early, negligible or early dark energy, it can be flatter curve, but all these models have something in common, which related to one of the questions I asked in the first talk, is that if you know the background, you can predict precisely what is the linear pulse spectrum, the linear growth. And that comes from the fact that if you take the Fourier transform of the 2-point correlation functions of overdensities and underdensities of dark matter, you got this expression. This comes from inflation. Another example how the early universe can impact late time observables. This is a mix because if you have massive neutrinos, this comes partially from the intermediate universe, but mostly from the early universe. Again, it's the coupling between baryons and photons, and this, the growth factor. This is a late time effect. And this, in these models, are first a function of time and a function that's completely determined by the background. So then what you test this model is not doing the background alone, it's not doing the perturbation alone, it's the cross-check between background and perturbation. So to do that, you need data, and I've been trying to get as many collaborations as I want. So I want to tell some of the collaborations I'm in to try to measure both the background and the perturbation. First, W1st, I'm a collide W1st supernova, and I'm a member of the Big Lens W1st. Back in last year, we published the state-of-the-art simulations of supernova in the W1st. This is a paper that involved Josh Freeman, Adam Rees, and a bunch of collaborators. The alphabetical starts here, so I did something for the paper, so sign. And using the simulation, we will try to answer these questions about the smooth dark energy paradigm, about these 4 hypotheses with Kurt working at Harvard, and that's quite important because if the smooth dark energy fails, then something quite exogenous is happening. For example, with gravity, etc. So we use the dark energy supernova and current constraints on Big lensing, and we show that the background, the W point will be so good to measure the background that if the growth deviates for more than 5% from the best fit of the SDM, this whole part of the models are gone. So let me repeat this, the background is so well measured that it can make predictions about the growth of structures to the 5% level. Even if you assume phantom, even if you assume arbitrary shapes of the dark energy. And the technique that we use to make such a general statement is the principal components of the dark energy equation statement.
What about the growth? The growth factor of gamma?
The growth factor, the G. Gamma is a parameterization of the big G, omega matter. Yeah.
You mean the function like the G that
Yeah. I mean more general. The second one is the dark energy survey. There's an interesting story between this in Brazil. I don't want to enter into politics, but I've been heavily involved in the dark energy survey, USA, not in the Brazil. And the archimedes is these three two-point correlation functions, shear, position, which I can explain for the students later. And the interesting of using two observers that you can break the general lines. You can see that from going from the green to the blue, you shrink the general lines. So I participate in this paper, and also I'm one of the leaders of the EDF spectrum paper that will be submitted on October 1st. It's alphabetical, so but I can assure you that my participation was very big. And one of the things that I explored was the relation between early universe and late time acceleration. For example, the relation between ineffective, which is an early universe radiation, with lambda. And with interesting conclusions, I'm prohibited to show the results of the collaboration with the second Brazilian collaboration. So one thing, the last one that I'm participating, U of A is a member of DESI, so I'm trying to enjoy the efforts, and I'm trying to advocate the following message. People have been asking in the United States why we need to spend billions of dollars to measure supernova and BAO at high redshift. So I've been very involved in asking these questions. And here I will try to answer the second question, why we need high redshift BAO. And the exercise we have done with this very general parameterization, PCA parameterization of WFZ, is to ask how dark energy and neutrinos are entangled. And the answer is quite a lot because counterintuitively, what makes neutrinos a bad feature of the CDM is the background. It's not the perturbations. It's a background, it's the distance, the ratio between the CMB and BAO, and I have a backup slide that can tell you this data. So the two conclusions that we reach in this paper that is being written right now is, this is the last slide, is the following. If dark energy is very general, the Coulomb constraints blow up to 0.8 eV. And here, I want you to pay attention just by the dashed line, which is the mean posterior distribution of the total distance. This is units of kilometers, not, this is dimensional, but there's no units of weight. So sheets like this is something that BAO can measure. Shapes like this is something that supernova can measure. And the difference between blue and gray is marginalizing over mu and not marginalized over mu. So blue is mu equals 0. Green is mu greater than 0. And you can see that they are the same ML redshift. And that's because if you have so much freedom in WFZ, you can just retweak WFZ to fix what BAO screws up. But that's not true at high redshift. A high redshift that you know dark energy. Therefore, even if you fix what the neutrino does at redshift below 1, you still have signatures at redshift above 1 that can be observed. Therefore, we should go towards high redshift. We should go towards redshifts where dark energy is important because a lot of stuff can happen between redshift 1 and redshift 1000. And one of the things that can happen, for example, is the transitions between relativistic and non-relativistic neutrinos is dark energy decaying other stuff, and all of that affects the Hubble function, and affects the total distance, the co-moving distance. So that's it. So I want to show with these blues of colors, each representing each of phase, that the universe is connected, and therefore, even if your research is only about dark energy, you have to be aware of what happened at other redshifts, because things got entangled together. So there's this quote from the Chinese Chuan Tzu, in went through PhD thesis that took me 10 years to realize how important it is. It says that it's the nature of things that they are tied to each other, and that's definitely true for the outer universe. Thank you.
Albite, can you show the type of size for the neutrino masses, low redshift, high redshift, and explain more how this relation comes about, distance,
Yes.
breaking of the lattices?
So, because it's a request, I can spend a lot of time. Okay. So, what's so special about neutrinos? So this is something. No. Here, it's here. How do I make something not a backup slide? Here. This is something that we work with just in Korea at University of Pennsylvania is the following. So the CMB fixes the amount of cold dark matter at redshift 1000. We quote that it's omega beta 8 squared because we assume some evolution of dark matter. Okay? What neutrino does is neutrino is pure radiation up to redshift of 200, and then it becomes dark matter. So at that point, it looks like there is some creation of dark matter in the standoff Columbus gap at redshift 200. And radiation is W a third, so there's W 1/3 converging to W equals 0, and that creates a jump in the D of Z that Yale doesn't like. If you revert that logic, one thing that can solve, that's why neutrinos predicts lower H0. Because if you make this curve, so this curve will go in this direction, and if you interpret this thing of this DM and extrapolate back to the CMB, it looks like you have higher omega beta 8 squared. But remember that omega beta 8 to 3.4 is fixed, so higher omega beta 8 squared is lower H. So because of this, I'm working just in Korean models where you do the opposite. You have dark energy decaying in something with positive W, because by just reverse logic, that makes H0 higher than it should be. There are problems with the integrated Sachs-Wolf effect that we are trying to solve, but this is a background effect. It's this conversion of radiation to cold dark matter that VO doesn't like. And that's why when you run an MCMC change, and you just do CMB, CMB is fine with neutrinos, but when you combine with VO, that you have a network here and here, things get wrong. And because it's a VAO effect, W can fix it. And that's the whole point of my paper before. More questions?
A philosophical question. All of these are, or most of these are null tests. You take a model, understand, or something, you try to do that. You see what happens if instead of making a null test, you want to measure things. Like measuring that without assuming anything. Like measuring whether it's modified gravity or not, without assuming things. I have the question, how many people are thinking about this problem?
It's because W is very far from observers. We observe double integral from W. We observe distance. That's it. Yeah, and so this we can try to do better with supernova because they're very fine redshift. But whenever you have, a decent big difference between what you predict and observe, it's going to be hard.
It's not possible.
Yeah.
But fundamental physics is not possible to do that. So I wonder, the question is philosophical, is not that reflect to anything. Isn't that the problem people should start thinking about how to measure things rather than only making tests to falsify?
That's true. And that's why I've been advocating very hard that one of the ways to measure things more independent, because you measure something and the amount of things that can change that observer come from all different redshifts. So we need to span our range of redshift observation. We think for a long time that going Z below 1 was enough, and I'm claiming it's not. Because otherwise, we couple that into a bunch of physics that we don't know. So I think we should spend $3 billion to build the successful of DESI. We should go to redshift 3 or 4. And that's why I think one of the reasons why I think cosmology in the 2030s will be very interesting, because there's a lot of stuff that can happen there that we just don't know.
And in all you've been talking about, you, for instance, you say a test perturbation given the ground, you're assuming this direction. So you're thinking of a test again.
Yes, yes.
So you see
I love
model independence.
No.
Really, it's a fundamental.
It's a personal belief. I don't think there's a model-independent test that's out. What you can do is relax some of the assumptions. Data don't give those answers. Data in a framework with physical input give us answers. We can relax some of that, but we always have some input. And with more data, you can ask bad questions. You can ask more complicated questions. So before, we could only ask, what about W? But now we can say how the physics of dark energy are robust against the physics of reionization. Just make that. So you can make more complicated and interesting questions because you have more unique data and a harder question range. But I'm one of the first people that don't believe that you always need some theory to test something. And I'm very suspicious of this paper. And I have used those words in mind, so I can say that say, oh, we're completely model independent. I don't believe that.